Well, thanks everybody, and thanks for organizing this, Sean. This is a really exciting opportunity to compare and explore new methods and see what everyone's working on. So good to see everyone down there. Sorry I can't be there in person, but good to see some familiar faces. So my name's Cunningham. I'm with the University of Alaska Fairbanks, but I'm also a core faculty member of the Alaska Salmon Program, or formerly known as the Fisheries Research Institute, that's based out of the University of Washington, that conducts research in Bristol Bay. And particularly, I lead our sort of preseason and in-season forecast team in collaboration with folks down at the University of Washington, Chris Boatwright, Ray Hilborn, and Daniel Schindler. And generally, you know, the methods that we use are all heavily reliant on the data that are made available through the hard work of folks at the Alaska Department of Fish and Game. So as always, a big thanks to those folks. You know, in terms of our Bristol Bay preseason forecast methods, they've evolved a lot over time. So I started working as part of the forecast team and leading our analytical efforts in about 2012. And over that time, we've had the opportunity to explore a wide range of methods that I'll talk about, compare their performance, and see how we can do better over time. Generally speaking, you know, as with most of these methods, our preseason forecasts are primarily based on the abundance of salmon returning in previous years, you know, what we think of as sibling relationships or cohort regression relationships, and a range of environmental covariates. And so these are things like sea surface temperature, as well as the abundance of potential competitors in the marine environment, thinking about interactions between sockeye and pink salmon for one. And, you know, as a reminder, these sort of sibling relationships, you know, are generally useful, or at least marginally informative, because fish that entered the sea in the same year experience similar conditions at ocean entry, early marine mortality, and similar freshwater conditions. So this, you know, the abundance of fish returning in a previous year is this nice proxy for their older siblings or individuals returning after an additional year in the ocean. In terms of our Bristol Bay preseason forecast as a whole, it's actually comprised of 38 individual predictions. So the 9 major river systems in Bristol Bay, with which everyone is fairly familiar. The 4 major age classes are 1-2s, 1-3s, 2-2s, and 2-3s. Plus, for the Nushagak River system, some folks might have noticed there's a non-trivial abundance of 0-3s and 1-4s, at least historically there have been. And so our process is similar sort of to the last speaker. You know, we have 7 candidate model structures, kind of 2 transformations of the data, whether we're looking in log space or not, and 2 different start years for our period of model fitting, either starting from 1963, kind of beginning of the brood years, or as Alec alluded to, thinking about whether or not we should just be representing dynamics after 1980, sort of post-PDO shift. And so individual model selection is based on kind of this comparison of retrospective performance over a recent 20-year period, looking at kind of 1 step ahead predictions. And so, you know, in general, you know, our basis for selecting a particular model for a combination of stock and age class is this sort of what we think of as expanding window cross-validation, right? So right at the beginning, using your entire data set, you can, at least in an ML context, tune all your hyperparameters based on the complete data, get your data through a given year, fit your model to that data, predict the next year, and repeat that process over your 20-year time horizon. And then at the end, for each of these stock and age class combinations, we have a similar process. We sort of sit down, look at performance metrics, so mean absolute percent error being one of them, root mean square error probably a better one, and then evaluate which has done well over the last few years and across this time frame. And also if there's any kind of persistent bias that's arisen in recent years. So thinking about whether or not system dynamics have changed, kind of thinking about conditions that we've observed. More recently in Bristol Bay, 2019 was a pretty interesting year, given the combination of extremely high temperature and low stream flows that seems to have had an impact on production from that brood year. So also bringing in a bit of that sort of domain knowledge. So in terms of the candidate models that we use or have used over time, you know, one of the the primary ones is sort of boosted regression trees. We also use a random forest approach, again, looking across predictor age classes, both within stocks and across river systems, as well as looking at a range of environmental covariates. We've looked at the sort of recurrent neural network approach and used that as a sort of candidate approach, again, primarily informed by return abundance of sibling age classes. In recent years, we've become increasingly reliant on the use of dynamic linear models. So taking your standard relationship between an older age class, maybe two twos here in the Igigik River system, predicting those as a function of 2-1 returns in the prior year, but allowing those regression coefficients to vary over time. And there's a couple reasons that this is, I think, particularly informative and useful in a forecasting context. Because so up here, this is basically just a plot for this relationship of the change in the intercept. So we can think of this as the kind of the average production or average run size across time. So changes in average production, as well as changes in that slope coefficient, that beta term, that would reflect a change in sort of the number of 2-2s you expect the next year per 2-1 returning in the previous year. And so, you know, if we do see a change in the intercept, that generally reflects a change in kind of average productivity or average return abundance across time. The change in that slope coefficient describing the relationship between the two age classes can reflect a couple of different things, right? It could be changes in marine mortality, changes in sort of the maturation schedule over time for many salmon populations within Alaska, at least, and elsewhere at a coastwide scale. We've seen this kind of changes in the ocean age of our aggregate return, sort of younger ocean age at return being pretty common. And so again, these sort of dynamic components within our kind of standard sibling regressions can capture some of that, even if we don't know the sort of provenance of that change. Tanya already spoke about empirical dynamic modeling. This is something we've explored in the Bristol Bay context, again, primarily informed by returns in neighboring river systems, but again, kind of looking at this association in time between observations that are kind of in the same realm and allowing us to generate some predictions. And then we use some of the autoregressive integrated moving average models that Josh talked about in this context, particularly in cases where maybe you're predicting 2 ocean returns off of jacks. The observation error for jacks, 1 ocean individuals, is pretty low. Maybe some sort of basic time series model can be a little more appropriate in that context. One of the things that I wanted to highlight is, so Dan Avando and I and others had a paper from 2022 in the Canadian Journal, and we looked at a range of these different methods, comparing them, but also looking at the importance of different kind of candidate predictors within a regression tree framework. And so this is for each of the major Bristol Bay River systems. What's plotted here is the importance of other features within that model. So of course, you know, for the Igigik River here, past returns to the Igigik River are the most important, but sea surface temperature, return year, so suggesting some changes over time, action of the PDO all came out as being important. For other river systems, other features like the abundance of chum salmon or pink salmon, returning to other regions came out as being important. So all to say that in terms of the useful information for forecasting, at least in a Bristol Bay Sockeye context, it's sort of beyond just the standard sibling model, sharing information amongst river systems, incorporating kind of North Pacific scale and localized abundance of potential competitors, and sea surface temperature all have shown to increase performance in some context. The other piece of the forecasting puzzle that we leverage is surface trawl surveys that are conducted by the NOAA Alaska Fisheries Science Center and the Alaska in collaboration with the Alaska Department of Fish and Game. These surveys generally capture Bristol Bay sockeye as well as other species of salmonids and other species more generally. They're carried out in September, October. And so this is an index of outmigrating sockeye in the northern and southeastern Bering Sea during September, October of the year of ocean entry. So this provides an index of juveniles that have survived freshwater, obviously, and sort of the first stage of marine mortality, at least that first summer in the ocean. The challenge with these data is one, there's a lot of spatial imbalance. That survey kind of skips back and forth, consistently sampling in the northern Bering Sea. The southeastern Bering Sea is variable amongst years, and overall the intensity of sampling across space has varied due to objectives and funding constraints. So we employ some spatiotemporal models to account for that spatial imbalance. But basically what I'm showing here is the predicted abundance density here for juvenile sockeye salmon across the eastern and northern Bering Sea regions, more yellow, kind of higher abundance, more blue, lower abundance. This is the year, obviously, in which the survey occurred, and then in red, those are the return years, right? Most of our Bristol Bay sockeye are returning after 2 to 3 years in the ocean. So you can think year of out migration plus 2 or 3 years. Gives you an index of abundance. Once you sort of look forward in time, sort of translate your index of abundance from an out-migration year, combine that across 2 out-migration years, and align that with your calendar year of return, you get a decent relationship on aggregate for Bristol Bay. So what I have plotted here is just Bristol Bay run size across time as these bars. Obviously, 2022 stands out as this record-setting year, 83 million fish returning to Bristol Bay on aggregate. The red and the green lines are just different ways that we can use that sort of high seas index of salmon abundance, again, associated with a given calendar year of return. And so you get sort of reasonable predictive power from a salmon forecasting context. In this case, survey data through 2024 informs our predictions for Bristol Bay run size in 2025 and 2026 and suggests something in the range of 43 to 53 million. So in addition to those sort of classical sibling-based and environmentally based preseason forecast methods, this index of juvenile sockeye abundance seems to have reasonable predictive power. And again, this works pretty well because the vast majority of sockeye salmon in the eastern Bering Sea are of Bristol Bay origin. That's not the same for Chinook salmon, chum salmon, other juvenile salmonids caught in that survey. So what have we learned, right? I think I said 2012 was the first year I kind of got interested and excited about engaging in the Bristol Bay forecast. The first is that times are changing, right? The sort of dynamic models, whether they're dynamic sibling models or allowing for interactions between sibling abundance and time in some capacity, and in regression tree framework, for example, seem to provide some benefit, kind of capturing changes in sort of average marine mortality or maturation schedules, and these have proved to be fairly useful in both Bristol Bay sockeye and Yukon River Chinook salmon contexts. Both machine learning methods, sort of the boosted regression trees I talked briefly about, and the dynamic linear sort of sibling models, both seem to improve forecast performance, but there's really no best method, right? The most accurate method really depends on the river system and the age class. So again, this process of sort of sitting down and saying, okay, on a river by age class basis, what performance have we seen and which model should we select seems to have some value. There's also appears to be value in incorporating information across stocks or across river systems in some cases. And these Bering Sea juvenile survey data provide this valuable predictor of Bristol Bay run size 1 to 2 years in advance. But there's also, of course, lots of challenges, right? One of the key challenges we've run into, particularly in application of ML methods for these data, are that we have the sort of conundrum of our wide or fat but not long data sets. Right, our unit of observation is the year. A long kind of brood table time series is 60 to 70 years in a salmon context. And so we end up with kind of limited scope for hyperparameter tuning. You can kind of bootstrap your data set to get around that to some extent. But I think that's kind of a persistent problem, at least from my perspective. The other one is that, historically in Bristol Bay, kind of thinking about the west side of Bristol Bay, Wood River, Nushagak rivers, large-scale shifts in production regimes usually aren't detected a priori or ahead of time. But some of these methods, right, if you have dynamic components, can account for them within 2 to 3 years. The other piece is that, while run size is our kind of primary focus today, most of our stakeholders care a lot about projected harvest, right? People want to know how many fish they can catch, and in particular, the size of fish they can catch. So, when we think this is our 2025 Bristol Bay preseason forecast, spoiler, it's 54 million. But in addition to that, we try to project the expected escapement in the given year, interception in other fisheries, and come up with a projection for inshore harvest. And then translate that into what folks really want, at least from a harvesting and processing perspective, which is the harvest in pounds. People want to know how many pounds of fish are expected. So that requires the combination of the sort of forecast here in millions of pounds, right? Which is the average or the predicted numbers at age times the predicted weighted age, and there's some relationship between weighted age and return abundance. So bringing all those pieces together can be a really fun and interesting part of the overall process. So really exciting to see all these methods and compare their performance, and more than anything, it's fun to see all these salmon forecast nerds unite. So excited for the conversations that are to come, and chat more with folks about potential methods.